Hello everyone, my name is Shibu Meher and I welcome you to the second lecture in this series on quantum information or quantum computing. In the last lecture, we discussed about classical systems and classical information. So in this lecture, we are going to discuss about quantum information. Before going into quantum information, you need to understand what is a quantum system. So a quantum system is a system that follows the rules of quantum mechanics. So one example can be an atom, where the electron in the atom they follow the Schrödinger equation. Similarly, in this lecture series, when I say about quantum system, we consider a system having some finite sets of classical states which are non-empty. We can have infinite set of classical state for a quantum system, but we're not interested in that now. We'll consider the quantum system to be having finite sets of non-empty classical states. Then similar to classical information and probabilistic states, we are going to use column vectors to represent this quantum system, and a particular state of a quantum system is called quantum state, and we use quantum state vectors to represent such quantum state. For example, let's consider this vector v, which is represented by alpha 1 to alpha n. So this is a n-dimensional quantum system. Each of this entry here is a complex number, and the only criteria that they should satisfy is that the Euclidean norm of this vector should be equals to 1. So what is the Euclidean norm? With the square root of summation of absolute value squared of each of the entry, right? So how do we find absolute value squared? We have to just multiply the complex number with its complex conjugate, right? So this Euclidean num should be 1, and each of these entries should be complex number. Then this column vector will represent quantum state vector, and each of these indices 1 up to n, they represent the classical state of the system. So similar to classical information, here we will have finite set of classical states, but the system can also be in some quantum states. Basically, if you have heard about superposition, so the quantum state can be in a superposition of these classical states at a particular time. But unlike the probabilistic state, which was also in some kind of probabilistic state, which is a linear combination of this classical state, we'll have some state that is really physical in quantum realm. So it is not like based on our knowledge or assumptions about the system, but it is actually a physical state of quantum system. And we'll see when we measure this quantum state, this quantum states collapses to one of the classical state with some certain probability that will be determined by Born rule. So we'll be discussing all about that. So let's take an example here, and we consider the example to be qubit state. So we have already defined what is a bit. It is a system having two classical states, zeros and 1. The qubit is a quantum bit. So it's a bit with some quantum properties, right? It is a quantum system. So it also has two classical states, zeros and 1. And it can be in a quantum state also. So similar to the classical example, we'll represent the 0 state to be ket 0 as 1 0, and 1 state to be ket 1 and it to be 0 1. So these are the standard basis state. Standard basis state. And we can represent the superposition state or quantum state, superposition quantum state, which we represent by linear combination of the standard basis state, and the coefficient here will be complex coefficient, and those coefficient will go into this column vectors, right? Okay, so let's define our quantum state. Let me represent that quantum state or superposition state as psi. So it is any abstract state, any abstract quantum states actually. So this, if I represent it as 1 by root 2, 1 by root 2, this means 1 by root 2 of 0 state and 1 by root 2 of 1 state. So this is a complex coefficient, this is another complex coefficient, but in this case the imaginary part is 0 basically. Let's represent some other state, phi, let's say, and we represent it as 1 plus 2y by 3 minus 2 by 3. This means 1 plus 2i by 3 get 0, and it should be a minus 2 by 3 get 1, right? So let us verify whether these two quantum states are following the rule of a quantum state. So what are the rule? All the entries should be complex, and this should, the Euclidean norm should be 1, right? So yeah, that's it. So let's see. So all these two coefficients are complex, the first will be satisfied, and if we take the Euclidean norm, these two number will get half plus half equals to 1. Similarly, if we take the Euclidean norm of these two numbers by 3 modulo square minus 2 by 3 absolute value square. So just, I don't know whether it is called modulo or not. Okay, let's not go into that. So it will be 1 plus 2i into 1 minus 2i, so it will be 1 square plus 2 square, so it is 5, and this is 9. Here the minus will be plus, is 4 by 9. If you see, it is 9 by 9, and hence it's equal to 1, right? So it is a valid quantum state. There are some other quantum state. So one we call the plus state. So it's a represent like this. So this is basically the plus state. This is a very special name. We'll see why it is important in the later chapters. So this is our plus state. Uniform superposition, basically having, okay, I'll talk about that later. And there is a minus state also. Let me write minus state here first. Minus state, and it has a similar kind of state, but there is minus sign in between. Okay, so now if we discuss a little bit about Dirac notation, this is our cat, right? So if we take complex conjugate of this, complex conjugate, we'll get a bra, right? So let's say this is our state, 1 plus 2i by 3 minus 2 by 3. So if this is our state, then our bra will be, then our bra of psi will be a row vector and the complex conjugate component here, right? So it was plus, it will become minus, and there is no imaginary part, so it will remain the same. So this will be our bra, and this we denote it as a dagger. This will become bra. This is a little bit about notation. So let's say we have a quantum state psi, and we want to know the coefficient associated with the zero state. So we do something called inner product. Then we can get the coefficient of zero state. So let's see how we get it. So zero state will be multiplied. We'll take the inner product with the psi state. It is 2 by I 1 plus 2i by 3 zero state plus it is minus indeed minus 2 by 3 1, right? So now as inner product is our matrix multiplication is associative, we'll just take 0 to both of the side and plus not both of the side, both of the component. It will become 0 0 minus 2 by 3 0 and 1. So here we'll get 0 0, it will give us 1, this will give us 0 because both 0 and 1 are orthonormal. That means if we represent them as AB, then it will become 1 when A and B are equal, and it will become 0 when A and B are not equal. So they are orthogonal and also normalized. Normalized means their magnitude is equals to 1. So we'll get 1 plus 2i by 3, which is nothing but the coefficient related to the zeros indices of this psi cat, which is the coefficient of 0 cat 0. Okay, so this is another this is a way to get the coefficient using a product. Similarly, if we do 1 psi, we'll get minus 2 by 3, right? Because this part will become 0 and this part will become 1. Okay, fair enough. Now let's go to quantum state of some other system. So let's say we have some other system where we have this set of classical states, and let's the finite number of A are there, A states are there. So if you want to, let's say, represent a uniform superposition for this system, we'll take a similar approach so that all of them have similar probability. Let's represent that as psi again. So this is the coefficient of each of the different classical state. These are the classical state, right? So this thing is the number of states in the set, in the classical state set sigma. Okay, now let's go and discuss about measuring. So we measure a quantum system with some basis. So let's discuss the measurement based on standard basis measurement. So what does this mean? We project the quantum state to some standard basis and we'll see what is the probability of that. Or basically, when we measure the quantum state, it will give us one of the standard basis. If we are measuring it in terms of some other basis, it will give us one of those bases, right? So what is measurement? So let's say we have a quantum state and we are doing some measurement. This will give us some classical state from the set of classical states, possible classical states, right? So it will just give one of them, it will not give multiple of them. So a quantum state can be in a superposition of different classical states, but when we measure them, these quantum states collapses to one of the classical state. So we have a rule called Born rule, which says that, let's say you have a quantum system psi, if you need a and B. So this is and this means A is the coefficient of 0, B is the coefficient of 1, cat 1. Then the probability that the outcome of our measurement is 0 is that A square, and the probability the outcome of our measurement is 1 is absolute value of B square. Why is that? Because the total probability should be equals to 1, right? And these are the two possible states we can have in this system. So in this example, so the absolute value square of the coefficient should be equals to 1, and each of the absolute value square represents the probability of the of occurrence of the corresponding classical state when it is measured. Okay, so based on this, we'll see that the plus and minus state that we discussed earlier, so it was 1 by root 2 0, 1 by root 2 1, minus 1 also 1 by root 2 0, minus 1 by root 2 1. So if you see, the probability of occurrence of 0 is half, and the probability of occurrence of 1 is also half. In this case also, probability of occurrence of 0 is half, and probability of occurrence of one state is half. So if we measure these states plus state multiple number of times, we'll get 50% of the time 0 state and 50% of the time 1 state. Similarly for minus state also, if we do a lot of measurements, we'll get 0 state to be 50% and 1 state to be 50% of the time. So we cannot differentiate between these two states. So in the next section that we'll study unitary operation, we'll see a special operation that can help us distinguish between these two states when we are doing the measurement in standard basis. So let's discuss about unitary operation. So when we discuss about unitary operation, let's compare both probabilistic and quantum operation. So our probabilistic operation and quantum operation. So both of them are linear mapping. This is also a linear mapping between input and output. This is also a linear mapping between input and output. However, probabilistic operations are represented as stochastic matrix, and quantum operations are represented as unitary matrix. So what's an unitary matrix? It's a square matrix U having complex number entries. Unlike the stochastic matrix, which was having real number entries, right? Positive real number entries. Positive real number entries, and the summation should be 1 for each column, right? For each column. However, in this case, the unitary matrix U and U dagger should give us the identity matrix. Similarly, U dagger U should give the identity matrix. This means U dagger is nothing else than universe. So here U dagger represents conjugate transpose of U, which is basically you're taking a transpose and then taking conjugate of each of the elements, complex conjugate of each of the elements. Okay, so one more thing, if let's say M is not square or not a square matrix, what is square matrix? Basically number of row is equal to number of column. Okay, that's a square matrix. Then if we find, let's say somehow M dagger equals to I, this does not imply that M dagger M will be equals to I. Is identity matrix. So here I is the identity. Okay. Also, because the because the U is a unitary matrix, if we apply U on some state psi, its magnitude, absolute value, will be equal to the absolute value of the state before applying the unitary operation. Okay. Okay, fair enough. That means, let's say yes, I represents a vector in the Hilbert space. When you apply u, it's just rotating the vector in the Hilbert space. It is not changing the length of this vector. That's what it means. So now let's see some examples of unitary operation. The first example is Pauli operations. So there are 4 Pauli operations. First is identity, and it is a 2x2 matrix 0 1. Then we have sigma x, which is also represented as x, so it will be 0 1 1 0. That's also called NOT operation. Then we have y, or sigma y, which is represented as 0 minus I 0. Then we have sigma z, or z. So this is called phase free operation, 1 0 0 minus 1. Okay, so if we apply this NOT operation, let's say on 0 state, it will give us 1 state, and if we apply it on 1 state, it will give us 0 state. That's a bit flip operation. If we apply, let's say z on 0, it will give us 0 without any change. But if we apply z on 1, it will change its phase to -1. It is basically 180 degree rotation around z axis. So we'll see that when we will be discussing about a block sphere, and how the quantum states are represented in block sphere, and how these different operations they rotate this block vector around the block sphere, and how do we get these kind of phases. So that we'll discuss in later video. Now let's go to other operation, which is a Hadamard operation. Hadamard operation, and we'll print it as 1 by root 2 1 by root 2 1 by root 2 minus 1 by root 2. So let's say if we apply Hadamard on 0 state, it will give us 1 by root 2 0 plus 1 by root 2 1, right? So this is a 0 state index, this is 1 state index. So what does it mean? So it's basically multiplying. So if we do not know how to get it, so it's just a matrix multiplication, 1 by root 2 1 by root 2 1 by root 2 minus 1 by root 2, and the corresponding vector you have to multiply. Let's say for the case of 0, it should be 1 0, right? So this thing will give 1 by root 2, and this thing will give 1 by root 2, and they both will be plus, right? Similarly, if we apply 1 to the Hadamard case, it will give us 1 by 0, and there will be a minus in this case because there is a minus here, 1 by root 2 1, right? And as you might be remembering, this is our plus state and this is our minus state. So applying a Hadamard operation to the 0 state gives us a plus state, and applying the Hadamard operation on 1 state gives minus state. Then if we apply Hadamard on plus state, then we'll get Hadamard 1 by root 2 0 plus 1 by root 2 1. Then let's take Hadamard to each of the states, as matrix multiplication is again associative. So 1 by root 2 as 0, 1 by root 2 as 1. So we'll get 1 by root 2 times 1 by root 2 0, 1 by root 2 1, and 1 by root 2, and this will give us 1 by root 2 0 minus 1 by root 2 1. So if we multiply all of them, we will get half 0 plus half 1 plus half 0 minus, sorry, this is going to be double line, half 0 plus minus half 1, right? There is a minus sign there, that will half 1. So we can cancel these two, so it will get to 0. Similarly, if we apply Hadamard to minus state, it will give us 1 state. Applying Hadamard to plus state, it is giving us 0. So one important thing to note here is that earlier we discussed that measuring the plus state and minus state directly in standard basis measurement, we are not able to distinguish between these two states, right? But now let's say you have a plus state and you apply Hadamard operation, you are getting a zero state. And let's say you have a minus state and you are applying a Hadamard operation and you are getting a one state. Now you do the measurement after applying a Hadamard on the states, then you will be able to distinguish between these two states, because this will give you 0 and this will give you 1 with 100% certainty. So that's a useful thing about the Hadamard operation. Now let's discuss about another operation called phase operation. So a general phase operation, which basically represents the rotation around the z-axis in the Bloch sphere. So we'll discuss this later, don't be confused now. So this theta is some real number, real positive number. When let's say theta is equal to pi by 2, we call this operation S and we represent it as pi by 2. This means 90-degree rotation. And in matrix form it becomes 1 0 0 I. So if you remember, it was I theta equal to cos theta plus I sin theta. So if you put pi by 2, it will sin theta will become 1 and cos theta will become 0. So it gives us I. Now let's say theta is equal to pi by 4. It gives us some operation called T. So it is pi by 4 and it becomes 1 0 0 1 plus I by 2. So if we put pi by 4 here, cos theta will become it will be root 2, 1 by root 2, and sin theta will also become 1 by root 2. So it will be 1 plus I by root 2. Now let's say theta is equal to 0, we'll get an operation called identity that we already familiar with, which is 1 0 0 1. And if theta is equal to pi, we'll get the operation called z, which is we have already discussed. Z also, which is sigma z, basically one of the Pauli's operation. 1 0 0 minus 1, right? Fair enough. Now let's see how this operation works and take some example and do some exercise here. So let's take a quantum state. Now apply, let's say, one of the previous operator, Hadamard, 1 plus 2I by 3 0 minus 2 by 3 1. So there are two ways to solve this problem. First of all, we know the matrix form of this Hadamard operator, and we can also find the matrix form of this quantum state. So we can do matrix vector multiplication and get the result. There is another way of handling this, is that we can take the Hadamard, we can apply it to the standard basis state, and then we can multiply the resulting elements, right? So we can 1 plus 2 I by 3, and it will give us 1 by root 2 0, 1 by root 2 1, then minus 2 by 3, and it will give us 1 by root 2 0 minus 1 by root 2 1. And I think this is a better way of doing it. So 1 plus 2 I by 3 root 2 0, 1 plus 2 I by 3 root 2 1, and this becomes minus 2 by 3 root 2 0 minus minus plus 2 by 3 root 2 1. Now let's combine zeros and ones and group them together. So it will be minus 1 plus 2 I by 3 root 2. So this one minus 2 0, and this becomes 3 plus 2 I by 3 root 2 1. Okay, similarly we can do another example. So this is our first example. Let's try to apply T on plus state. A similar procedure you can take T, you can decompose the plus state to be 0, half root root 2, 1 by root 2 1. So So this t you can apply on the first segment. So it is 1 by root 2 t0 plus 1 by root 2 t1. So if you see this matrix of t, it will take 0 to 0 and it will take 1 to 1 plus I by root 2 1. So let me write them down here. T0 will take it to 0, T1 will take it to 1 plus 2 I think I by 2, right? 1 plus I by root 2 1. Okay, you can verify it if you want. Just put the column vector for 0 and 1 in that matrix, in front of that matrix, and multiply them. Now you can get 1 by root 2, 0 is 0, so it doesn't require anything. So 1 by root 2 into 1 plus I by root 2 1. It becomes 1 by root 2 0, and this becomes 1 plus I by 2, and 1 remains 1. So this is one simple example how we are going to apply quantum operation to quantum states. Now let's discuss some other concept called compositions of qubit unitary operation. So compositions means basically matrix multiplication of multiple unitary operations or quantum operation multiplication. So for example, let's say there is an operator R, or let's say let's not consider like this. Let's say you applied Hadamard operation to a state, then you applied the S operation to the sum state, the resulting state, and again you applied another Hadamard state, and let's call this R. This means we'll just multiply the matrix to get the resulting operation or unitary matrix resulting from these three operations, and 1 0 0 I, and here also 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. So if you multiply this, we'll see some matrix like 1 I, 1 minus I, so there was 2 I divided by 2, 1 minus I divided by 2, 1 plus I divided by 2. And one peculiar properties of this R matrix, unitary matrix, is that if you take the square, that is multiplied twice, then it will get the not operator, which is basically our X operator, right? Sigma X we call it. So R is the basically square root of the not operator. So this kind of operation, this operation is not possible in a classical system of single bit. Is not possible in a classical system of single bit, but this thing is possible in quantum system. We can have such kind of unitary operation for a large system also. So let's take an example of permutation operator. Let's consider a system whose states set are 1 2 or 0 1 2, let's say 0 1 and 2. So and define a unitary matrix 0 1 0 0 0 1 1 0 0. So what it basically does, it takes the 0 state to the 1 state, it takes the 1 state to the 2 state, and it takes the second state or 2 state to the 0 state. So it is basically permuting or doing a permutation, rotating the states between them. So this matrix is called permutation matrix. So one of the simplest permutation matrix is our identity, which is simplest. So we can write a permutation matrix for a system or for any positive integer dimension, and it can be any positive integer dimension. You can write a permutation matrix. Just shift the zeros from the Unitary Matrix by 1, like it is done for this case. So this is the only example of matrix, the permutation matrix, and represent both classical operation, classical and quantum operation basically. So it is only a matrix that is both stochastic and unitary. And also in another way, you can say if a matrix is both stochastic and unitary, it should be a permutation matrix. Another example of unitary operation in large system is the 4x4 quantum Fourier transform matrix. This is a very important matrix, and it can be defined for any arbitrary dimension, any positive integer dimension basically. So it's looks as follows for 4x4 dimension: 1 1 1 1, here also 1 1 1, I minus 1 minus I minus 1 1 minus 1 minus I minus 1 and I. And it's very important transformation in all of the quantum algorithms, most of the quantum algorithms. So that's it for today about quantum information. Thank you for your attention, and I hope you will subscribe the channel and stay tuned for the more videos on this topic and more of the technical topics in science, technology, engineering, and mathematics. Thank you for your attention. Bye, and see you next time.